Good morning, everyone. Today, I'm excited to present our work on mutual pairing data augmentation for few source continual relation instruction. This research addresses critical challenges in continual learning for NLP tasks and propose a novel data augmentation approach. So let's begin. Here's what we'll cover today. First, I'll introduce the concept of few source continual relation instruction and its challenges. Then I will explain our proposal solution, highlight our key contributions, set experimental results, and conclude with insights gained. So let me introduce to few source continual relation instruction, or FCRE for short. So relation instruction is tag in information instruction that identifies semantic relationship between entity and entity pairs in text. For example, in a sentence, Steve Jobs was born in San Francisco in February 24, 1955. We can extract the relation born in between Steve Jobs and San Francisco. In a few source continual relation instruction scenario, models must continually learn to identify new relation types from very limited data while retaining knowledge about previously learned relation. This creates unique challenges that traditional approaches struggle with. So FCRE face two major challenges. The first one is catastrophic forgetting, where models forget old relations as they learn new ones. And the second one is overfitting, where limited data per relation leads to poor generalization. So existing methods typically store samples from previous source in memory buffer, but with minimal data streams, they will struggle to maintain a performance across all relation types. So now let's look at our solution to these challenges. So the core idea of our approach is surprisingly simple yet effective. We pair sentences from our trained data to create new augmented trained samples. So here's how it works. We generally select a pair of data instances from our trained sets. So we concatenate the pairs to form a single input text. So each augmented sample preserves the original labels of each component sentences, as known as original single label space, while creating new label space called dual label space. This dramatically increases the volume and diversity of our training data without requiring external resources. So to effectively leverage the augmented samples, we developed specialized objective functions. So the first is our margin loss for the 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 original single label space shown here. So this loss function ensures that we have different relations in our paired sentences. The model learns to distinguish between their respective representation. This helps the model focus on relevant information while ignoring noise. So our second objective function is this contractive loss for the dual label space. This brings a new perspective to training by considering pairs of relations at unified entities. So it encourages the model to learn that augmented sample with the same set of relations should have similar representations, while those with different relations should be distinct. So our final objective function combines the base model loss function as well as L0 with our proposed margin loss and contrastive loss weighted by parameters beta 1 and beta 2. So this comprehensive approach allows our model to benefit from multiple training perspective. So we also explore softness aware minimization as a technique to improve generalization. Interestingly, we found that applying SAM to all training data sample was less effective than applying it only to current tag data, same current. This provides valuable insights to future research in field source continual learning. So now, let's look at our experimental results to see how our approach performs in practice. So we evaluated our approach on 4 benchmark datasets, FCRE and TAGRET for relation extraction, and Maven and ACE for event detection. We used BERT and LM2VEC as the backbone models and compare against state-of-the-art baselines. So our first results shows the accuracy after training on each task from T1 through to T8 for different methods on FCRE and TAGRET datasets. The highlight rows represent our method, and you can see the significant improvements in both final accuracy and forgetting rate. For example, on TAGRET, our best method of 61.97% accuracy after the final task, outperforming the baseline by 2.49%. So the second result highlights how our method improves SAM performance across different datasets and baseline methods. So for instance, with CPL using LM2VEC, our approach archives 73.38% on TAGRET, a substantial improvement over both the baselines and SAM alone. So the graphs further illustrate how our augmentation strategy consistently enhances performance across different configurations. So particularly when combined with current tag only SAM approach. So our final results slide extends our evaluation to field source continual event detection and on ACE and Maven datasets. The trends observed here further confirm the effectiveness of our approach across different information extraction tasks. So when combined with SAM, our data augmentation method consistently improves performance, demonstrating its versatility and droppiness. So let's now summarize our findings and discuss implications for future research. So in conclusion, our key contributions include a novel mutual pairing data augmentation strategy that effective combat data scarcity in FCRE, specialized loss function that enhanced model training for multiple perspectives. So valuable insights on applying SAM on field source continual learning scenarios. So our approach significantly outperforms existing methods, advancing the state of the art in this challenging field. We do note limitation. Our augmentation method can amplify the disparity between current and past tasks, potentially biasing the model toward relations when batch sizes are limited. So thank you for your attention.